Why hello friends, Jen Foxbot here. Welcome to another edition of Math Mondays, da 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 da, yeah! Alright, thanks for joining me. In this episode we are going to talk about derivatives, yeah! Specifically, derivative calculus, heck yes. So, I've talked a bit about why derivative calculus is super cool, but not so much on how to do them. So in the first part of this video, we are going to look at a simple example of a car traveling over a distance and use derivative calculus to find the speed of the car. And we will generalize our work to figure out the power rule of derivative calculus. And then in the second part, we will look at three other specific rules in calculus, derivative calculus, the product rule, the quotient rule, and the chain rule, and I'll briefly touch on some of the other common derivatives. So here we go. Okay, part one. Let's start with a question that most of us are familiar with. So let's say I leave my house and I travel to a friend's house, and I want to know what my average speed was during that trip. Because let's say part of the way I hit really bad traffic and the other part I was cruising. And so I want to know how badly did the traffic affect my average speed. Let's say I was on the freeway and I should have been traveling at 60 miles an hour, but the traffic slowed me down. How much did it slow me down? Well, let's figure that out. Okay, so first we need to create a plot that represents what we did. And so in that case, I'm going to draw it over here. So the first thing is my house is at the origin. Since this is my plot, I can do whatever I want. And then now we have to figure out, okay, so we are saying that I left my house and I traveled 5 miles and it took me a half hour. So now we need to figure out, if we're going to draw this, what goes on the axis? Well, typically on the horizontal axis, you put the independent variable, and in this case, that's time, because unfortunately or unfortunately, we cannot control the passage of time, so therefore time is independent of how far we traveled or whatever other things we happen to do during that day. Time keeps on marching forward. And since we're looking at this in miles per hour, sorry to my friends abroad, I know the US system is not as easy as a metric system, but this works the same even if the units are different. Okay, and then on the vertical axis, that is my dependent variable, and in this case that is distance traveled. Let's see if I can find, for a variable, I'm going to put C for car, and you'll see why I'm picking this kind of weird variable in a second. But this is going to be in miles. And the reason why this goes on the vertical axis is because how our speed, or well, I guess like as the car is moving, our distance is dependent on time. Where we are in the world depends on time. We can control this, we can't control that. Okay, so now that we have our plot mapped out, we can actually draw what happened. Well, okay, I guess I should erase that first. So I know that this is my ending point. This is my starting point, 0, 0. That's my house. All right. And then I end at 5 miles, 0.5 hours. And let's say that wait, that doesn't make sense. Okay, let's say that my actual path was maybe more like that, but I'm interested in the average, so that means that I can just draw a straight line and assume that my average speed is constant. It doesn't change depending on the way that your path looks. So the average speed would look like that. Okay, and now we have a straight line. So we're like, aha, we are wizards in figuring out the equation of a straight line. We know that we use y equals mx plus b. In this case, b is 0. And so instead of y, we have c. Instead of x, we have t. So c equals m times t. And what is m? Well, m is rise over run, and in this case we have 2 data points, so we can find the slope. And that's just going to be y2 minus y1 over x2 minus x1, where this is x1 comma y1, and this is x2 comma y2. And so in that case, it's going to be a half an hour, 0.5 hours. My dog's drinking water right here. Cute. 0.5 hours minus 0, divided by 5 miles minus 0. That's going to be 0.5 divided by 10, or 10 hours per mile. Okay, so that is our slope. So then we can write our equation. I'm going to write it up here. So the distance that we have traveled equals 10 hours divided by miles. Whoops, that kind of looks like it's times t. Okay, so now this is where we pull in derivative calculus, because what derivative calculus allows us to do is to find the rate of change of a particular thing. In this case, it's speed, because speed is how fast our distance is changing over time, or how much our distance is changing over time. And so in this case, we want to take the derivative with respect to t, because that is our independent variable. And so what we would do is we can use this notation, which is very common. This is why I didn't pick d for my variable. So we want to take the derivative with respect to time of our equation c, which is a function of t. So then we just plug in the equation for c, which is just 10, my miles, I guess I don't need to keep writing that, times t. Okay, and then this is where we need the power rule. Okay, I'm gonna make this smaller actually. I got very excited and I wrote a very large data point. 5 miles, comma, 0.5 hours. Okay, so the power rule in calculus says that the derivative with respect to a variable, I'm gonna write this here, of a general form of a times x to the n, where n is some number and a is some number. They are constants, they don't change, it's just a number. This could be 5 and that could be 2, that's cool. This is just a general formula. So when we take the derivative with respect to x, what we get is we bring n down, so n times a times x to the n minus 1. So we subtract 1 in the exponent, and the exponent comes down to multiply to the front of our variable. So here we have t to the 1, and so this just equals 10 times 1 times t to the 0. And so t to the 0 just goes to 1, and so this equals 10. That's it. Pretty cool, right? And so this actually is our speed, our average speed. That's it. So I am a little confused by the units, so I'm gonna skip that for a second. It'll probably come to me as soon as I stop recording the video, because that's usually how it goes. But basically what we have found is that our speed equals 10, our average speed is 10 miles per hour. Yeah, cool. So again, sorry about the units thing, I'll have to think about that for a hot second. But what this has told us is that the rate of change of our equation is 10. So our average speed was 10 miles an hour, and to answer our original question, did the traffic affect my average speed? The answer is yes. I was traveling way less than 60 miles an hour. I was only traveling about 10 miles per hour. So on side streets, you might be cool with that. But if you were on the freeway, you'd be like, heck no, that was so slow. So that is how we can use calculus apply it to our own lives and ask some really interesting questions and actually seek answers. So yay, math. Okay, so that is the power rule in general. And this applies to any of the values of n, so it works for fractions. So if you have a root x, that also can be written as x to the 1/2. And so you can plug this into that formula. Interestingly enough, you're going to get negative 1/2, which would just be, so x to the negative 1/2 would just be 1 over root x. And so in that sense, you can also use negative numbers in the power rule. Just make sure you subtract, so negative 1, which would be, oh my goodness, I'm running out of space. So if you have 1 over x, that equals x to the negative 1. And so just subtract, it would give you x to the negative 2. X to the negative 2 is just 1 over x squared. So the power rule is very powerful. So sorry, terrible math pun. Please let me know if you have any questions about that. And if you want to learn how to do more derivative calculus, check out part 2. Yay!